question was, why is this not starting? Yes. Well, the question was, what about expressions? Why do we need to learn about expressions? And we said expressions are they are very simple concepts, or they are based on a very simple concept of what needs to be executed at what time and in what order. And we said, okay, this is very simple. The idea is expressions will actually generate values, and they won't actually do any side effects. So this means that when we define these expressions as in a recursive form, like saying, okay, expressions can be simple literals or variables and operations on those sub-expressions. When you have such a thing, then you're already defining what is supposed to happen, right? So when there is no, if I say, okay, an expression is some operations with, let's say in a binary case, with a binary operation, something like this, and when I say there is no, let's say, side effect, but just a return value, then I'm already kind of semantically saying something about what this can do and what this can do and what they cannot do, and in turn also what order I can actually run them in, right? So in this case, for example, if I assume that this is actually following, this language is following the strict definition of an expression, you'll say, okay, I can actually evaluate E1, sub-expression E1, and I can evaluate sub-expression E2 independently in any order I want, because there will be no side effect of anything to anything. And then I can combine them with that operation. But this will also bring us another question. If you can do these things in any order, do you need to actually execute those things to get that value? So do you need to execute or evaluate that expression at any given time? Can you delay that till you need it? So this brought us the concept of normal applicative order. So this is applicative order. Where is this? So we said the applicative order evaluation assumes that, this is a simple concept again. What we do is, in order to apply an operator as part of an expression evaluation, I will first evaluate the sub-expressions that is needed by that operator. All right. So the sub-expressions are evaluated first, no matter in what order they are needed or whether they are needed or not. So I don't ask the question, would I need some of those operands later on, the values of those sub-expressions later on. Now, this of course brings us the question, sometimes in some cases, you might, let's say, encounter the cases where you have some operands, some sub-expressions are not needed by you. That may arise, that may come because of some reasons. For example, we'll see several expressions. In that case, the question is going to be, can I actually delay, or can I actually delay these evaluation of these operands or sub-expressions till I need them? This is a nice concept. Why would I do that? Why would I actually delay the operands or the sub-expressions evaluations? Efficiency, he's saying. He's saying, why do we need to actually evaluate something if you don't need them? Evaluation means here, when we say evaluation, when we say actually give control of the CPU to actually get that value, it means a work to be done. And work requires time, or the CPU cycle, and perhaps memory and so forth. But we are saying that here, we are assuming that an expression isn't in its pure form, meaning it doesn't do any side effects, so memory would not be an issue, hopefully. And then in that case, the question is going to be, do I need to actually steal cycle from the CPU to do that evaluation? If I don't need them, I shouldn't. This is one place. Another place that could happen is that it may be that that evaluation cannot be done in, let's say, real time. Meaning, for example, if I am actually calculating an, let's say, something that will give me value till, let's say, I have an expression and I have an unbounded array, an infinitely unbounded array. This is what my language actually allows me to do that. Now, I know that I can never generate an unbounded array using my computing capabilities. But I can have the concept there, and I may not need to actually get to that end of that, let's say, there is no end to it, but unbounded array, but I may need to go into it as much as I need. In those cases, especially functional languages use this lazy evaluation, which we'll call it later in a few minutes, concept to define these unbounded or infinite, let's say, ranges or infinite arrays or something like that. So this is there is another use that, yes, CPU cycle is one thing, and the memory space for memory is another thing that you can actually use non-strict evaluation, or you can defer the evaluation of your, let's say, expression to a later time, and that later time will probably never need that unbounded array anyway. All right. So we said if you have a side effect, you cannot do that, this strict evaluation. This strict evaluation says I can actually do this in any order I want, right? But if you have, let's say, like in C, if you have an expression like this, right? So this can be an expression. This is an assignment, but let's assume that this is an expression, or we can actually have something else like this. For example, x plus x equals 10, something like this, right? This is a valid expression in C, but this expression has a problem, meaning C actually doesn't enforce the expressions to be side effect free. There is a side effect here. We know that if I actually do the order, let's say if the value of x is already, let's say 9 here, starting with 9, the result of this, if I am doing this from left to right, the start of this is going to be, the value of this is going to be 9 plus 10. This will be 19 in one case. And if I actually do this from right to left, or do this one first and this sub-expression first and then this sub-expression second, then the result will be 20. So these type of, let's say, definitions, if you have side effect free expression semantic implemented in your language, this would always give you one value, regardless of where you start from. So you can do the left sub-expression first or the right sub-expression first. Whereas here, since there is a side effect, C allows this side effect to happen in its semantic, in expressions. Therefore, this will be actually, you have to define an additional rule for this one. C will say, okay, do this with a right associative with operator and do this from left to right, for example, and then return the value. So here, the order of operations is going to become an important thing. All right. There are other things like sequence operators. Many languages have these type of things. A sequence operator will actually start from one of these expressions, the first expression, second expression, and so forth, till the end of that expression. And then it will return the last expression's value. If this is a side effect free definition, then you can actually do this one first, because I know that expression 1 and expression 2 will not affect the result of this one ever, because they are never going to actually do any side effects. Of course, C doesn't do this one. But some languages do this. Notably, many functional languages will actually have this possibility. All right. So this sequence operator or the order of operation in a side effect free definition will actually be useful. But then if this is useful, why do I have it, right? That depends on the other constraints that the designer of the language has to consider, right? So perhaps efficiency was an issue there, and they actually chose a definition or chose a semantic like that. But the idea here is that if I have this semantic implemented this way, I can now communicate with you easily. I can say, okay, no side effect here. Then done. He knows that now I can explain easily the order of operations. Doesn't matter. They can be in any order. And I know that there is no side effect. So many of the, let's say, constructs that I can use, like a sequence operator or just a simple expression, recursive definition of expression, is defined by just these two simple assumptions, by saying there is no side effect and it returns, an expression returns a value always. Of course, this doesn't explain you it explains only the value, but there is also, if you recall, the other, several courses or classes we have discussed the type of these values. So typing is another issue that we have to talk about when we talk about expressions, but assuming that that's not a big deal for the time. All right. Now, non-strict evaluation says, okay, evaluate an expression without necessarily evaluating all the sub-expressions of it. As we said, if I have an expression in the form of E1, some operator E2, then this says, okay, I have two sub-expressions, this one, and then a binary operator. All right. Now, I'm assuming that I can actually delay the expressions evaluation of these and actually apply operator before I can actually apply get the values. This is a little bit of a difficult concept to realize, or let's say imagine, because we are thinking mostly in terms of strict evaluation or applicative order evaluation by now, because of the languages that we have learned or you have learned. This concept of actually how do I delay things? How do I delay so that I actually know the need? For example, if I have, let's say, x plus y. What does x plus y means in terms of non-strict evaluation? It says, okay, we delay it, apply or evaluate the expression before you are evaluating the sub-expression. What does this mean? This means that you try to apply this operator first. That is needed to actually evaluate the value of this thing. Now, it requires the value of this guy versus and value of this guy. Now, one way of thinking this would be, you say, okay, in order for me to actually generate this, I will need the value of this guy and this guy. Now, I will evaluate them. This is non-strict evaluation, right? I still do the same thing. The effect is the same. Whereas, let's say, in the other case, I say, okay, before looking at this guy at all, just look at this guy and get their values, and then consider the operation. Now, depending on the operation's type, perhaps I can actually now do something. I say, okay, I'm going to do a addition. I have two values, right? Or let's say multiplication. Let's change this to a multiplication. I have two values coming to me. And the first value, I evaluate the first value because I need it. But I delayed the evaluation of the first value till I decided what to do. So I am doing a multiplication, and I'm looking at my first operand. And let's say that the first operand is 0. Now, if the first operand is 0, I don't need to actually evaluate the second operand. My result is already 0. Or vice versa. Could be I may be doing the second operand first. But once I actually realize that one of those operands are, let's say, 0, I don't need to actually evaluate the second operand. So this is one way that you can actually use non-strict evaluation. All right. So there are several cases that this happens. We have seen these type of things in the past. For example, short circuit Boolean expression, right? And if expression and case expressions, right? So let's take the case expression, right? What you do is you actually will do the second, third, or fourth, let's say, cases only if the first one fails, and then second one fails, and the third one fails, and so forth. So, for example, a C-style short circuit evaluation, you have this something like this. If false and X, or if true and X, you can short circuit these easily. No need to evaluate the second one, because the first one is going to define what it is. All right. And then, like these if expressions, if you have the test expression, so if you think that if is an expression, by the way, in C, if is a statement, not an expression. That's why we call it a statement. Here, if you think that if is an expression, like let's say in Lisp, so if you recall, Lisp will do it this way, or something, let's say some languages, it will test the expression, and depending on the expression itself, if this is a function or it's an operator, it will actually do the first expression, or it will do the second expression. Again, this is not a statement, this is an expression, right? So if this was an eager or applicative order or strict evaluation, you would be evaluating this one, and then this one, and then you'll be actually choosing which one to actually evaluate based on this one, right? So this is a form of a non-strict evaluation. Again, if you treat if as a expression, not as a statement. All right. We have that, if you recall, in C, you have this type of a thing. This operator, this is an expression. This will generate either the value of E2 or E3, but it has actually three sub-expressions. The first expression is here, the second expression is here, and the third expression is here. So it will generate the first expression, where this is not a statement, this is an expression. So the value of this expression is going to be done not in a strict manner, meaning it will actually do this one first, and then depending on the value of this one, it will either evaluate this guy or this guy. If this was a, let's say, applicative order thing, it would have need to be actually be doing the, perhaps this guy will do actually E2 and E3 in any order, and E1 as well. Okay. So statement is a different thing. We know that. We are going to come back to the statements again. And we said statements are actually different than expressions. They are not generating a value, but they are actually generating a side effect. So their concepts are different. These two concepts are quite different from each other. Right? So when there is no side effect, what we can do is we can do this normal order evaluation or lazy evaluation. Expressions usually evaluated in mathematical form this way. So the operation is evaluated before the operands are evaluated. So again, in this case, I do this multiplication operation before I actually need the values of E1 and E2. And then I decide what to do about E1 and E2. It's a slightly different thing, but it's conceptually quite different. So in the other case, in the strict order evaluation, or let's say applicative order evaluation, what I'm doing is, no matter what the operator is, I'm actually doing the operands first. I get the operands, and then I apply the operator. Here, I apply the operator, and I get the operands. Now, in order, for example, if the operand is a multiplication operation, then I know that I cannot delay the operation of those sub-expressions. I have to get the values of those sub-expressions. perhaps in any order that I want, but I need those values. Okay, if you look at actually, let's say these two functions, and we can actually look at them in applicative order evaluation. This is how it is going to happen. Let's say you'll do actually square. So let's say, what am I doing here? I'm trying to get the square of double 2, right? So I have a square of double of 2. So in the case of actually normal order evaluation, I'll get this guy. To be able to get this guy, I need the double 2 and double 2. And I will actually get, to get the double 2 and double 2, I will actually get 2 plus 2 and 2 plus 2. And then I will actually get the results this way. All right. So this means that to get the values, what I'm doing is I'm kind of expanding all the operations till everything is actually written in this form, 2 plus 2 times 2 plus 2. And then now I need the values, then I need to actually evaluate this entire thing. You can see this as a normal order evaluation. If this was an applicative order evaluation, when we say square double 2, I will get the double 2 first. I will need to actually get the double 2. Double 2 is 2 plus 2, and I will get that value, and I have the square 4, and I'll get actually square 4 is 4 by 4, and that will be 16. The result are the same, but the execution order of things are quite different. You can see that already. So, of course, this is good, especially in the case of things like, let's say, macros and in imperative languages. But if you have side effect, this will not work. When you have a side effect, because this order of things here, when you actually define this one and you do this one versus you actually do this one here 2 times. So this says, okay, I'm getting the double 2 twice. That function code is actually evaluated twice. Whereas here, this function code is evaluated only once, right? So these are the difference. You can see that efficiency-wise, they will be different. But also, if you have some side effect on the double 2, then this side effect and this side effect will actually probably give you 2 different results here. So in that case, you have to do applicative order. But where would you actually have a, let's say, advantage of this one? The advantage will come, for example, if I don't need the second double 2 at some point. So I'm not actually evaluating that. So I'm actually just pushing this till I decide when I need them. And this could be also, as I said, an infinite call to a recursive, let's say, an infinite recursive call. So by actually eliminating that infinite recursive call, when I need something, I say, okay, do this till, let's say, 10th iteration, 12th iteration, 100th iteration. I can still do this, but conceptually, I can define this as if it's an infinite, let's say, value. So this is one of the places that you can use this quite well. All right. Now, assignment operators. They have to imply side effects, because assignment says, okay, I'm taking a value and I have, let's say, a variable or some memory that I represent another value, where I represent another value, and I change that. Right. So this is a general concept in imperative languages. You cannot assume an imperative language without an assignment statement. You have to have it. There is no way out of it. So pure functional programming will probably have no assignment statement at all. Pure ones will not have. But then the question is going to be, I have to return a value from my, let's say, language. And that value is what your, let's say, expression actually prints out at the very end. So your entire programming is going to be actually evaluating let's say, an expression. Could be a function, could be multiple functions, and so forth. And usually the syntax is actually you have a target variable, an assignment operator, and an expression. And there are a couple of ways that actually people use this with a single equality or an equality preceded by a column. All right. Of course, there might be the cases where you have the overloading of these operators, and you might have some languages overloading these operators. Okay. For example, conditional targets, you might have conditional targets. So your assignment operator might have a conditional target on the left-hand side. This is usually we don't have this in C type, let's say, languages, but this is possible as well. So you can condition your left-hand side operand for your assignment statement with a condition. So here you see that this operator or this expression, if you think that it's an expression or consider this expression returns a variable instead of, let's say, a value, right? So you can say, okay, maybe a variable is considered as a reference here, therefore it's a value, but in it. So you need to actually discuss or decide declaration order. How do you declare them? Where do you declare them? In what order? And then binding. When does this binding take place, right? So you have to, we discussed those things earlier. So you might have compound operators. So these are now moving away from our pure definition of expression. Now what I'm doing is I'm putting an expression inside a statement. So I'm combining those. And you know, for example, a plus equal sign will give you a compound operator. This is quite common in many languages, especially imperative component of those languages, including C, C++, Java, and so forth, JavaScript, and so forth. Might have unary assignments like again, these are kind of compound things, like plus count and plus and minus and so forth. Some languages like C and Perl and JavaScript assumes that assignment is also an expression, meaning the assignment statement is now. So this is conceptually kind of a difficult thing, right? So you are saying, okay, I have an expression, I have an assignment, and I'm actually having something that actually combines these two. So this is some of the things that we discussed earlier, like orthogonality of features. So these are kind of mixing those, and these features are not necessarily orthogonal themselves, because you can actually do some of them with the others and so forth. All right. Multiple list assignments. There are some languages like, let's say, Perl and Ruby, and I think Python has this thing as well. So you can do assignment with a single assignment sentence or a single statement. You can assign multiple or list assignments. And statements are simple. Statements, again, in their pure form, they will actually return no value. So you cannot actually take a statement and use the result of that statement as an operand or as a sub-expression to another expression. And typical of these are selection statements and loops. All right. So the idea with these one is actually you would create the effect, the side effect, inside these statements. So when you have a statement versus an expression, let's say this is an expression and this is statement. So expression will return a value. You have to use that value somewhere. So that means that either as part of another expression, or at the worst case as a return value of a function, or even as a worst case as a right-hand side operand of a assignment operator. Whereas a statement will actually do something. It will not return any value. The value, return value of a statement is not defined. So there is no typing information associated with it. But it will actually do something in your state. It will perhaps change a variable's value. It will change maybe an output. It may consume an input and so on. All right. Any questions? We are going to come back to this non-strict evaluation, the lazy evaluation, a little bit when we discuss procedures, and we have a way to actually pass a value from a caller to a callee, and we'll discuss this again there shortly. All right. So any questions? If there are no questions, let's continue with, we have 10 minutes, 13 minutes, we can still do exceptions. All right. So one thing that we are going to discuss is, I could have discussed this after the procedures and function calls and so forth, but I think this is the right place to do this. So we were discussing how we actually evaluate things, how we actually execute things, in what order, right? So we discussed two things, simple things. One is an expression and one is a statement. Statement was doing some sort of, let's say, side effect, and expression is returning a value. So these are the simplest two concepts that we have. Now, the question is, what happens if there is something, if something goes wrong? Either during the expression evaluation, let's say you are doing applicative order evaluation of an expression, and your first operand to a multiplication actually failed somehow. We don't know why it has failed, but it may fail. Similarly, if you have a statement, some part of the statement might actually fail. So the question is, what do we do when there is a failure? What type of mechanisms do we have to actually handle those? Right? So first of all, what are these? We call them structured exits. Exceptions are structured exits. There is something going on, perhaps hardware related, perhaps software related, something the machinery actually generates some things. For example, if you are trying to evaluate a partial function with your expression or with your statements, and when you have a case where your input is not actually mapping to an output in that partial function definition, then you have to actually stop your program, because you cannot generate a value. That function is not defined for that. So this is the, let's say, one case. Or something happened. For example, let's say you run out of memory. These are, again, concept-wise, not part of, so far at least, we didn't discuss these type of, let's say, limitations in our semantic so far, but these are realities, right? So I may have, for some reason, or I will have a limited amount of memory, and for some reason, my program might actually run out of memory. What do I do in those cases? Or maybe even worse, maybe simpler, perhaps, or better, or maybe easier than the, let's say, the other cases, you might have hardware issues, right? So somehow hardware actually fails. We didn't discuss it so far, but we are assuming, let's say, even if we are assuming a von Neumann model, maybe there are things that underlying model actually doesn't, let's say, maybe they are implementing some partial functions again. So division by zero, for example, right? So what do we do in these cases? So we need to terminate part of a computation, all right? So the things that we need to do there is we need to jump out of the construct that we are in, expression of a statement. And ideally, we may need to actually pass the data as part of our jump. We need to exit that situation. We are in an expression. I was multiplying two numbers. And then somehow the first number actually calculation or multiplying two sub-expressions, the first expression actually gave me a exception, meaning it is trying to actually evaluate, let's say, a partial function, and it cannot. So what do I do? So I jump out of that because I cannot actually stop there. I mean, I have encountered an error. Now, this error is not part of my expectation of that expression. That expression is supposed to be returning a value, but I cannot return that value. Okay, what do I do? So as I said, I will need to jump out of the construct, and I need to actually pass the data as part of the jump, so that whoever actually executed or tries to execute that particular expression needs to know about this. Otherwise, if I don't actually tell you that, then I have no idea what went wrong there. So I can actually try to continue as if nothing happened. And then where do I return? Do I return to the most recent site that is, or recent site that is set up for handling that exception? Okay, so we need to decide these things, and for this type of structured exits, we have two main concepts. One is we need to declare and establish some sort of an exception handler. This is where you come to once actually that things happen, once that jump out is happening. And we need to also have a way of actually telling or letting the, let's say, program execution that something happened, something regarding or something that actually caused a structured exit or exception happened. So these are statements or expressions that raise or throw an exception. There are examples of this one, you know, from C and C++ and so forth. But then the question is, what does this mean semantically, right? So this has been quite, I mean, this has been a hot topic in language design, programming language design. And some people said, okay, the question is, how do I terminate? Do I terminate? When something goes wrong, you have two options, right? You say, okay, something went wrong, and this is, whatever I do after this will be out of the semantic that I define. For example, I was expecting this expression to return a value. Now it's not going to return a value. So one option is just terminate. Say, okay, I'm done. I don't know. I don't care. I cannot actually do this calculation. This is not defined. And it's not my task to actually do anything. So I just stop it. This is termination. Alternative is you try to resume. So you say, okay, I know something happened, but I will let my programmer, or let's say the rest of my program, therefore the programmer, decide what to do about this. So this is the resumption or resuming, resumption semantic, termination semantic versus resumption semantic. And they have been discussing this, I mean, they are still discussing these things. And Mitchell, one of these guys, that has been working on language design for a period of 20 years. He's saying that termination is preferred over resumption. This is one option, and he's for this because he says this is not a matter of opinion, but a matter of years of experience, he's saying. Resumption is seductive but not valid. So his idea is that resumption, you want to fix things, but if things are undefined, how are you going to fix them? So hoping to fix things doesn't mean that you can fix them, or doesn't mean that it is correct to fix them. So he is on the pro side of termination semantic. He says, okay, we need to terminate, right? Okay. Another part is they are saying, okay, no, you have to actually resume, right? So I have a lot of in beginning of my This is slides. I have a lot of quotes from this guy. And he's saying that, okay, it has to actually have a certain, let's say, so let me see. So he's saying that there are a lot of features and notational conventions, many of them unnecessary, and some of them like exceptions handling, even dangerous. This is also saying that the exception handling is dangerous. Do not allow this language in its present state to be used in applications where reliability is critical. So this is the reliability thing. And reliability has a lot to do with actually these loopholes that you can create by exception handling. And they consider this as creating a hidden control flow paths that are not actually available when you actually look at the code. So this is again an idea, or let's say an idea against resumption. You can see this, right? So I'm looking at the code. The code says, okay, I have an exception here, expression here. I have an if statement and whatever. I can see what's happening there. Now, all of a sudden, I have to actually go on the side and look at that code again from the perspective of actually what would happen if I need to actually, if I have some sort of exception handling mechanism. So that's another control path. I have a regular control of the thing that I need to understand. Hopefully, I am kind of making it clear with expressions and statements and so forth. Now, I have a third one here, or a second path that will depend a lot on the, let's say, the runtime effect of the things. So most of these exceptions are going to come at runtime, or all of them are going to come at runtime, because if I know that they are going to come at compile time, I will kind of, let's say, program them for those, so I can actually get my logic right. But now I am actually opening another path, which is different than my logic for my program. So people find this a little bit difficult and dangerous to actually think in terms of two complexities, just rather use the first complexity. Okay, anyway, so this is still an ongoing discussion. What do you like? Do you like exception handling? Would you rather terminate or resume exception? Resume. Who is resuming? Come on, come on. Raise. I cannot see your hand. Up, 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 up. Exercise. 5, 6 people. What happened to the rest? Okay. Termination. We should terminate. Almost the same amount of, or less number of people. The rest is not interested in programming at all. What are you going to do? When you encounter with a exception, what would you do? Unless your, let's say, boss or your other colleagues are actually enforcing them, are you going to just say, okay, no, yes? Yes. Resumption var. When you actually have an exception handling, you are assuming that you are doing, okay, so putting the mechanism in there, giving the possibility to actually resume. So if you have an exception handling mechanism, you are actually for, first of all, the language design is for handling it, for resuming it. But as a programmer, you can actually do termination as well. You can say, okay, whenever I see an exception, I have a catch. Let's say in Java does catch or what? Catch. So Java says, okay, my handler is going to be just exiting. So this could be your choice. But many languages these days will have some sort of an exception handling mechanism. So from that perspective, Java's design is actually encouraging, perhaps, resumption. But the programmer may or may not actually use it. All right. So let's look at let's take a break. And we'll continue at 2:30. Sorry, 3:30.
Hocam, by the way,
yes.
In the beginning of the class, you said
Bir dakika arkadaşlar, duyamıyorum.
You said 30% of the classes you should attend in school. Is it still